Okay, so the Legendre equation, the Legendre polynomial is going to be the solution of this. And the last time we wrote d over dx 1 minus x square dp over dx and plus L into L plus 1 minus m square over 1 minus x square p was equal to 0. This was the Legendre equation, and in this equation we assumed azimuthal symmetry. Azimuthal symmetry was that the potential remains the same if you go along a circle around the sphere. A circle in which theta is not changing, only phi is changing around the sphere. Then we say that this term will be equal to 0. And our equation will reduce to d over dx 1 minus x square dp over dx plus L into L plus 1 p equal to 0. So under azimuthal symmetry, our equation will get this form, and we can rearrange our equation like this, that 1 minus x square p double prime means the double derivative of p minus 2xp prime plus L into L plus 1 and p equals 0. Now the solution of this equation we considered in the form of power series. So if p of x is equal to summation on k, which is running from 0 to infinity, ak x to the power k plus alpha. If we consider this is the solution of this equation, then we come to know, it means by finding out p prime, p double prime and putting all this in this equation, then we got the first two terms of this is a naught alpha and alpha minus 1 x to the power alpha minus 2 plus a1 and alpha plus 1 and x to the power alpha minus 1 plus the rest of the terms I wrote in terms of k runs from 0 to infinity. So that these were the first terms. So the next term will be a2. In a2 I write then ak plus 2. So when k will be 0, the next term will be a2. And the rest of the equation is k plus alpha plus 2 and k plus alpha plus 1 minus ak, and this is k plus alpha and k plus alpha plus 1 minus L into L plus 1, and this is enclosed and enclosed again for this one. If I enclose here as well, then one enclosure is for here and the other enclosure for here, and x to the power k plus alpha, and this thing is equal to 0. So this was the solution of our equation, means our equation, when we put this power series, then this equation converted into this one. the first two terms mean the lowest powers k0 and k equal to 1 we wrote like this, while rest of the terms, the high powers of x, because you see here the high powers of x, here x means k will be equal to 0, 1, 2, 3 and so on. So the high powers I wrote in this form, only the first two terms I just put the values. When you put the values k equal to 0 and k equal to 1. So for these two values k0 and 1 we put the values there. Now these two terms gave us the situation that individually all terms are supposed to be equal to 0. We considered this one equal to 0 and it gave us some values of alpha and a0 as well. Similarly, this one was considered equal to 0 and we got some values. Then we will consider the final term equal to 0 as well. So let me write that for the first term to be equal to 0 means the discussion on this one is a bit technical and little bit you can say it is to be elaborated more to understand this one, that what we are doing means you will have to keep in mind that this is the differential equation which you are going to solve. How you will solve this differential equation? The solution you consider in the form of power series, and the power series converted this differential equation into this form. Now you took the two values out of it and the rest of values you wrote in the summation. So what you are going to find out? You are going to find out these coefficients a0, a1. These are the values which you are supposed to find out. You are supposed to find out the value of alpha, that what this will be. And here you are supposed to find out the values of n and 12 plus 1, because this was the solution of your differential equation. And we are just behind this one. So the first one, when you write, if the first term is equal to 0, means a0 alpha into alpha minus 1 x to the power alpha minus 2, this is equal to 0. Then you know that this one will not be equal to 0 because this is your variable. Your coefficient should be equal to 0, because 0, then you can write that a0 alpha into alpha minus 1 is equal to 0. And this gives you that if you consider that a0 is not equal to 0, if there is f, if a0 is not equal to 0, then it means this one is equal to 0. So you write alpha. This implies that alpha into alpha minus 1 is equal to 0. And then this gives you that either alpha is equal to 0 or alpha is equal to plus 1. You can write that for the second term, means what will be another way? Another way will be a0 is equal to 0. So if a0 is equal to 0, then you don't need to say these things. Similarly, the next term, which is a1, and this is alpha into alpha plus 1 x to the power alpha minus 1 is equal to 0. This implies this one is non-zero, so this thing is equal to 0, the coefficient equal to 0, a1 alpha and alpha plus 1 is equal to 0. And if you say that a1 is non-zero, this a1 is non-zero, then it implies that alpha into alpha plus 1 is equal to 0, which means that either alpha is equal to 0 or minus 1. Right? Either alpha is equal to 0 or minus 1. we will write here now that we will disallow alpha equals -1. Why? Because look here, for this one, if alpha is -1, then this will be x power -3. Here it will be x -2. Now when this will become, so it will become 1 over x3, it will become 1 over x2. So at x equal to 0, this will diverge, right? So we say that we want the series to converge, because if the series will be diverging, then you will not get the solution of your equation. The solution will only be possible if your series converge. So you say that we are not allowing that alpha is equal to -1. So you are having the possible values of alpha is 0 and +1. These are your possible values. Now, because this one is creating divergence at x equals 0. Now what about the higher values of k? We got, means from the first two terms, we got some clue about our coefficients. We got some clue about alpha. Now for higher powers of x, it will give us a recursion relation. For higher values of x, we will have a recursion relation for all values of k. How? When this whole term will be equal to 0, then you can write that when this whole term is equal to 0, then you can write that means the summation, no need for a summation then, because the summation has nothing to do with equal to 0. Means this minus this is equal to 0, and you can write that a k plus 2 into k plus alpha plus 2 and k plus alpha plus 1, this is equal. When this term is equal to 0, then this will be equal to this term, which is equal to k plus alpha and k plus alpha plus 1 minus L into L plus 1, and this is multiplied with ak, this one. So this is equal to the positive of that, and from here I can write that ak plus 2 is equal to k plus alpha plus 1 minus L into L plus 1 whole divided by k plus alpha plus 1 and k plus alpha plus 2, and here you can write ak. And this is called the recursion relation. Why the recursion relation? What is a recursion relation? Because you will give value here and you will get the next value, right? You will give value here, like for example you write k equal to 0, then it will become a0 and it will become a2. So you got a2 in terms of a0. If you give here ak equals, means k equal to 1, then it will be 1, and what it will be? A 3. So what you are getting, you get a 2 in some terms of a naught, or you get a 3 in some terms of a 1. Now here one thing is clear. If your initial value is an even value, means a naught is even, a1 is odd for k odd. So for even value here, you get even value here. For odd value here, you get odd value here. It's not possible that here the value will be odd and you get even. So your series is actually a sum of odd and even coefficients, right? And this means this is recurring. It will give all the values. You give here a 3, you will get a 5, a 4, and a 6, and so on. So this is called a recursion relation. Now there is a big question, and the big question is that you should know the value of a naught and a 1. Right? If you don't know the value of a naught, then you don't know the value of all even coefficients. If you don't know the value of a 1, you don't know the value of all odd coefficients. So this is very important to know the value of a naught and a 1. That was the reason that we expanded the first two terms, and the rest we wrote in the form of recursion relation. Like if I say that how much is your height, and you say that I am just 2 inches taller than the other person, and I ask that person, he say I am 3 inches lower than that person, and so on. Now I will not know the height of any one of you unless and until I know at least the height of one of you. Once I came to know the height of one of you, then I will, you can say, do calculate for all of you. So this is the same situation. If I know a naught, I will have all the even numbers here, because that can be from the recursion relation, you can calculate that. If I know the value of odd here, I will have all the odd values. So now we will focus ourselves that in order to start with this series, we should know the values of a naught and a 1. So what should be those values? Okay, let's start here that our recursion relation is going in step of 2, because you see with every number 2 is being added. So it jumps in step of 2. So we will have is recursion relation. So I will write RR for this one. Recursion relation goes in step of 2. So we will have either odd powers of x or even powers of x, because means the coefficient is also deciding this power as well. So we will have either odd or even powers of x. Now let's say if we say if a naught is equal to 0, if I say that a naught is equal to 0, like here, means we were having the supposition that a naught is non-zero. Now if a naught is 0, then a1 should be 0 or non-zero? It should be non-zero. Otherwise, if you say A naught is 0 as well as A1 is 0, then your whole thing goes to 0.